finding domain and sometimes range without a graph. Our discussion of function notation has made us very sensitive to the equations behind the functions we work with. However, you've been focusing almost entirely on domain and range from a graph, whether the graph was discrete, consisting of a finite number of points, with a discrete domain and range, whether it was continuous and infinite but bounded, with a bounded domain and range, or a graph whose domain was all real numbers. You may very well be asked to find the domain and occasionally the range from looking at the equation and studying the equation and not necessarily seeing the graph at all. Think about and review what we saw when we looked at example number 3. I chose the equation y1 equals 1/2 x squared minus 2, entered it into my calculator, hit zoom 6, and showed you what I got. You can confirm if you want that y1 equals 1/2 x squared minus 2 does give us this graph, although until we study polynomials in more detail, there's no reason why you should know how to find this equation yourself. However, what we saw in the graph was that the graph got wider and wider on either side of the x-axis, and therefore we concluded that the domain was all real numbers. Does this agree with what we know about the equation? Let's save that for later. We also saw that the graph got higher and higher, starting at 0, -2 going up, and 0, -2 going up on the other side. And because of that, we concluded that the range was all real numbers bigger than or equal to -2. However, does the equation agree with what we just found? In the case of y equals 1/2 x squared minus 2, the graph did match the equation. The details of the equation exactly appeared in the graph. However, beware. There are times when the calculator can miss small but important details that affect your answer. Algebra is much more reliable and never misleads. So let's look at the algebra. First, when working with domain, we start by trying to make the domain as large as possible. We want the domain to be all real numbers if we can get that to work. After all, if we're going to the trouble of making a function, we want to use it for as many x's as possible. So the domain ultimately will include every x in the real number system that will allow us to find an answer when using that x. An x that makes an error is not an answer and therefore cannot be in the domain. There are many functions that never have an error and that make their domains be all real numbers. They're error-free because they use multiplication, addition, or subtraction, and you can't get an error from doing these operations. Check it out. Constant functions, where y is always equal to a specific number, no matter what x is, will give us a graph that's horizontal with slope equals 0. Linear functions that have the formula y equals mx plus b, where m is not 0 and the line appears to be slanty, is also domain all real numbers because all we're doing is multiplying our x's by a number and adding on another number. You can't get an error doing that. Polynomial functions are in the same situation as linear functions, except the exponents, which mean multiply, can be more than one. The equation 1/2 x squared minus 2 from example 3, is a polynomial function. That is why the domain was all real numbers. There's no number in the real number system that you can square and get an error. You can divide it by the number 2 and you can take away 2 and you will get an answer every time. And since the smallest x squared we could possibly make is 0, and the smallest y becomes 0 squared divided by 2 minus 2 is -2, we can understand why the range goes from -2 to infinity. Absolute value functions are another example of functions that never have an error. You can put any number you want inside an absolute value bars, and when they come out of the absolute value bars, they make a perfectly nice answer, just not negative. You can multiply them by a number, you can add on a number. You'll never get an error. So what does that leave? What symbols or operations will make a function have an error? The answer is division for one, square roots for another. Division will always make an error if you divide by 0. So any x that makes that happen, that makes the bottom of a fraction equal 0, will make the answer disappear in an error. So if we make f of x equal x divided by x minus 3, then x minus 3 can't equal 0 for f to work. And therefore the domain of f is all real numbers as long as it's not 3. Square roots will have errors if you put a negative number inside the square root. Any x that makes that happen can't be in the domain. So if g of x is the square root of x minus 3, then x minus 3 must be bigger than or equal to 0 in order for the square root to work. And if x minus 3 is bigger than or equal to 0, then the domain for g must be all real numbers, provided they're bigger than or equal to 3. Now that you know that fractions and square roots have errors, and you know how to find them, you can now answer any question that asks for the domain simply from function notation. We are going to have an entire unit on graphing fraction equations called rational functions, and finding the range of this is not a simple matter. However, finding the range of g of x is really not that difficult, because square roots can never have negative answers. So as long as we're allowed to put almost any number except for 3 inside of here, it's pretty much certain that the range for g will be bigger than or equal to 0. You can put it on your calculator and check it out, but you may have an opportunity to see one of those little discrepancies between the calculator and reality.